Okay, for this question here, we've got this complex number z, which is equal to 1 plus cos 2 theta plus I sine 2 theta, where theta is between negative pi over 2 and pi over 2. And for a part 1, we have to show that the arc of z is equal to theta. So if we've got a complex number z, a plus bi, then the arc of z is equal to arctan of b over a. So arctan of the imaginary over the real part. Okay, and we also have to just make sure theta is going to be between negative pi over 2 and pi over 2. So that arctan of b over a, that doesn't always tell us exactly what quadrant we're in, because tan is positive in both quadrants 1 and 3, and negative in both 2 and 4. So if our denominator, a, is positive, then we're either going to be in quadrants 1 or 4, which would be between negative pi over 2 and pi over 2. So let's just set it up with our question here. So we've got the arc of z then is going to be equal to arctan of sine 2 theta over 1 plus cos 2 theta. So this then is equal to, now we can just use some double angle identities here. So sine 2 theta, I've got them written in red over here, is equal to 2 sine theta cos theta. And 1 plus cos 2 theta, if we use this identity here and just take the 1 over to the other side, it's going to be equal to 2 cos squared theta. Okay, so we get this. And that denominator is actually always going to be positive, cos squared. So between negative pi over 2 and pi over 2. Okay, now we can just go about simplifying this. So we get arctan of, well, the 2's will cancel, and one of the cos thetas will cancel. So we're left with arctan of sine theta over cos theta, which is equal to arctan of tan theta, which means then that that is equal to theta. So we've proven then that the arc of z is equal to theta. Okay, and we are between negative pi over 2 and pi over 2. Now for part 2, we have to show that the modulus of z is equal to 2 cos theta. Okay, so what we can do is we can just apply the formula for modulus. So that means the modulus of z is going to equal the square root of 1 plus cos 2 theta squared plus sine 2 theta, and that will all be squared as well. So we can expand and start simplifying this a little bit. So then we're going to get the square root of 1 plus 2 cos 2 theta plus cos squared 2 theta plus sine squared 2 theta. Now this part here, cos squared 2 theta plus sine squared 2 theta is just equal to 1. So then we're going to end up with, I'll just write this step here, you can kind of skip this one and go straight to the next one. 1 plus 1, that's equal to 1, plus 2 cos 2 theta, just to make that very clear there. And then we're going to get 2 plus 2 cos 2 theta, which is equal to, well, if I factor out this 2 here, I'm going to get 1 plus cos 2 theta. And now I can just use our double angle identity. So that would be this one here. I'll just write it in red over here. So if we had cos 2 theta, well, that is going to equal 2 cos squared theta minus 1. So therefore then, as before, we get our cos 2 theta plus 1 is going to equal 2 cos squared theta. So now putting that into our expression here, we're going to get 2 times 2 cos squared theta, which is equal to 4 cos squared theta, and that is equal to 2, and square root of cos squared theta is just the absolute value of cos theta, and now that just equals 2 cos theta, and we know that because theta, we're told, is between less than pi over 2 and bigger than negative pi over 2. So cos theta is always going to be positive on that domain in quadrants 1 and 4. Okay, so we have shown then that the modulus of z is equal to 2 cos theta.